Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a postdoctoral researcher currently at the Helsinki Institute of Physics over in the University of Helsinki in Finland. And I'm a cosmologist, so that means that I study the universe, the contents of the universe, how everything evolves, how everything interacts, all of the cool stuff happening inside the universe. Obviously, I don't study everything, just a subset of it. And yeah, I love being a scientist and I love chatting to everybody about all of the cool things that happen in the universe, about science, about academia, about space, everything. This is a general Ask Me Anything. For anyone who's new here, welcome. For any return viewers, welcome back. Always great to see you. And I see people already saying hello here in the comments. We have Ange, we have Aegis, we have Paul, Pratt. Nice to see everyone coming back. Really nice to see all of you again, as always, every week. Great to see everybody here. So I don't have a special topic today. For anybody who doesn't know how this works, this is an Ask Me Anything about the universe. Basically, an Ask Me Anything, specifically the universe, but you can just ask me anything you want, and I will do my best to try to answer those questions. If you've ever wanted to know about space, about dark matter, about gravitational waves, about time, about wormholes, about the cosmic microwave background radiation, all of these questions, feel free to ask. If you want to know about academia, about science, about living in Finland, about putting ants in a microwave, this is an Ask Me Anything. And if you've just joined, please do like the video, subscribe if you haven't done so already, leave a comment down below. All of these things actually really do help boost engagement, and then I get more views, which means I can talk to more people about the universe. And I should remember to breathe. So yeah, this is an Ask Me Anything. You can ask anything you want. Holiday weekend. Nice. It is not a holiday weekend here. So I know it's a holiday weekend in quite a few places. It's like Memorial Day in the US on Monday. It's a bank holiday in the UK, I believe. In Germany, Monday's a holiday. But it is not a holiday here, which means tomorrow is a usual work day for me. But for all of you celebrating a 3-day weekend, that is great. I'm glad. Enjoy your 3-day weekend. 3-day weekend should be the norm. I am very much a fan of 4 days of work and 3 days weekend. The 5-day work week is an antiquated system that needs abolishing, but that is a whole other tangent that we're not even 3 minutes in and I'm already going on tangents. Is microwaving ants our new thing here? I mean, it's not our new thing, but it is a thing that I'm now very interested in. It was a very cool topic. I've looked up some videos. I mentioned it to colleagues and everyone's like, wait, that's really cool. So yeah, ants are small enough that they could theoretically hide in the nodes of microwaves where the waves meet and actually not feel any effect. So technically, ants and things smaller than ants can actually survive being microwaved unless they're touching hot food, because then the heat would do serious damage. So in general, just don't put ants in a microwave. It's probably not like a good hobby. I'm sure you can find better hobbies than microwaving ants, but technically ants can survive a microwave, which is a very cool fun fact I learned last week, thanks to people asking me what happens when you put ants in a microwave. And when I say ask me anything, usually I mean things that I actually know stuff about, but if you ask me stuff I don't know about, then we also get fun stuff. So 8-hour workday is pretty antiquated as well. I completely agree. Yes, it makes no sense that we're supposed to spend a third of it every weekday working. Like, that's not what humans were designed to do. We are designed to sit around campfires and tell stories and be social creatures and help each other and live in communes, and instead we have to deal with capitalism. But anyway, microwaving grapes makes plasma. I have never tried microwaving a grape. That sounds like a fun thing to try and less damaging than microwaving ants. So yeah, microwaving grapes sounds like a fun experiment. Do you then do you eat the grapes afterwards? Do they turn into a mush? Like, what happens? Do you get the same effect if you microwave a tomato? I'm going to start microwaving random things in my kitchen and see what happens. But yeah, I've never made plasma in the microwave before. That sounds fun and a good way to kill the microwave, and probably a sticky mess. So I guess you put that on a plate, not just put the ants in directly. So only the ants smart enough to stand in the right place survive. Well, I guess, if ants, like most creatures, kind of like surviving. So if there's a very hot area, they would move to the colder area. Then there was the question, the follow-up discussion I had with another scientist of, would they actually be able to get to the cold spot quick enough, or given their small overall surface area, would the heat already be too much? But technically, I think they would have enough time to find the right spots to hide in. Okay, I see an actual physics question, because ants are fun, but ants are not my topic. We should get Isa Betterbug in for Isa from the bug scope to talk about what would happen to ants in a microwave. We could do a joint stream on that. Okay, how close is the LHC to reaching the energy levels that existed during the Big Bang before expansion? Was there an event that triggered expansion that could be detected by LIGO? Ooh, two very, very cool questions there. Okay, the LHC, the Large Hadron Collider, is a particle collider in CERN. It's underneath Switzerland and France, and it is smashing particles together at very high energies to reproduce the conditions of the early universe. However, it is not quite there yet because the early universe was very, 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 very energetic. So that means that you would need to go to very, very, very high energies in order to reproduce this. And currently we can go quite a way back in time, but not yet that far back. So we are gradually increasing the energy of the Large Hadron Collider to push it further and further back in time. And I just want to add the caveat here that when we're talking about high energy, some people get worried, like just how much energy are we putting into the system? But it's very high energies for the individual particles. But in each collision at CERN, so each time you have protons smashing together, there's about as much energy as in a lightning bolt. So it is a lot of energy, but it's concentrated in a small space. But it's not something that is in any way dangerous or something you need to worry about. So the Large Hadron Collider is currently, I believe, going through more maintenance, and then it's going to start with the biggest one. Or is it already started the next one? There's going to be a new one reaching new higher energies, but it will never be able to reach the energies that were almost like right at the just after the end of inflation. And the energies before inflation, that's something that is way, way, way out of our foreseeable future. But there are plans for a future circular collider, which is a much bigger version of the LHC, which would have 100 kilometers. So Large Hadron Collider is 27 kilometers of tunnels underground. The future circular collider would be, I believe, hundreds of kilometers, and it would use, like, if the LHC is here, it would go around. And then it uses the same it would use the LHC as like the pre-accelerator, and then it would feed into the big one. And that one would push us to very, very, very close to the energies that were around not long after the end of inflation. So that would be a very, very cool thing to do. And hopefully we'll have the future circular collider someday. It's still not clear if that's going to be funded, and if so, when that's going to happen. I'm not actually sure if it's partially funded by now or it's still planning phase. But yes, the future circular collider will get us slightly closer to Big Bang style energies. And there was a second part to your very good question there. Was there an event that triggered expansion that could be detected by LIGO? So what triggered the expansion of the universe? This is always a very good question. So when we talk about the expansion of the universe, I'm guessing here you mean you're referring to the first expansion of the universe. So if we consider the standard picture of the history of the universe, this image that a lot of you have a cool name for, you see that if we go to the far, far, far left, we have this Big Bang, then we have inflation, debatable which of these you call first, that's just a nomenclature, a naming issue. But you have this initial stage of accelerated expansion. But we also know that the universe is undergoing accelerated expansion today. The accelerated expansion today is probably caused by dark energy. The accelerated expansion in the early universe is what we call inflation. And this inflation could have been caused by many things. We're not completely sure what triggered it, but the fact that we have inflation is very cool because it helps us explain some open questions we had in cosmology, like why does everything look the way it does? Basically, inflation gives us a way of explaining why the cosmic microwave background radiation, this thing here, looks the way it does. This is the oldest light in the universe, CMV, background everywhere you look. It gives us a snapshot of what the universe looked like in its infancy. And the different colors here, the blue and the orange ones, correspond to tiny, 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 tiny temperature differences. Very, very tiny temperature differences. But beyond these tiny temperature differences, the overall temperature of the CMB is exactly the same in overall directions. So these differences are like 1/10,000th of a degree, 1/100,000th of a degree. So they're very tiny temperature differences. So this means that overall, this is at an average temperature of 2.73 degrees Kelvin in whichever patch you measure. And the reason that it is almost the same temperature was a bit confusing, but inflation helps us explain this because at some point everything would have been close together. It could have balanced out the temperatures and then it inflated. But your question was, is there any event that caused this? We're not completely sure. Could LIGO measure this? Now, LIGO probably couldn't. This period of exponential expansion, this inflation period here, could have produced gravitational waves. Now, gravitational waves are ripples in the fabric of space-time. And we've already measured gravitational waves from black holes smashing together using LIGO, the Laser Interferometry Gravitational Wave Observatory that we have here on Earth and its companion Virgo. And we've measured gravitational waves coming from black holes smashing together. But these are more energetic than ones that will be left over from the Big Bang. So inflation itself could have produced gravitational waves, but these are beyond what LIGO could measure. To measure these, we would need to go to space with LISA, which is an upcoming mission that will launch within the next 10 to 15 years, hoping to find the gravitational waves of the very, very, very early universe. And I love that your question there could allow me to talk about a lot of different topics. And I know I'm not going too in depth with a lot of the things here, because I'm just leaving these as like breadcrumbs that you can pick up on and take us down different tangents if someone wants to ask more about gravitational waves or the CMB or LISA or LIGO or black holes. Here's just some random topics that you are welcome to ask about. And yes, indeed, it took less than 10 minutes for the CMB to appear today. You always have to remind yourself that these color differences are really just showing tiny, tiny, tiny actual differences. Yeah, when you see the CMB, we always show these color differences here. Right, and we always say, like, okay, there's colder spots and there's hotter spots. The cold spots are in blue, the hotter spots are in orange. But this difference is so small. We're talking about 0.00001. So that's of a degree, right? So it's such a tiny, tiny, tiny difference that really this is basically the same temperature. It's these really small differences. It does look like big cold spot, big orange spot, or big hotspot, but that's not the case. These are really tiny, tiny, tiny temperature differences. Hey, Scott, nice to see you. Great to see you here. No worries if you can't catch the whole thing. It's always good to have you while you're here. Okay, going back to the questions, because I know you all asked a bunch of good questions at the same time. So now we're going to go through all the questions. And as always, if I don't answer you immediately, I'll try to answer you at some point during the stream. Usually by the end of the stream, I try to answer all the questions. What happens if I click on the favorite button? I've just seen there's a favorite button here on the comments, and I've never seen that before. So just out of curiosity, I'm going to see what happens if I click that. Oh, I can pin messages. Huh. That is cool. I've just learned something new about my Restream interface. I can pin messages, but then they go to a separate screen, so then I lose them. So that's kind of weird, but good to know. Good to know that a year into using Restream, I am still learning things. James, I can see that comment. You're not being ghosted. I think I've replied to your comments, and I was about to read out a question that you asked. So yes, I definitely see you. And I'm going to go back to the questions I've missed. How big is the false spectrum in the CMB colors compared to the size of the range of visible light? So the range of visible light goes basically from like 450 to 850 nanometers. So there you're talking about a difference in wavelength of the order of nanometers. Whereas what you're talking about here in the CMB is a difference of like so small, like a really, really tiny difference. I just got completely distracted by the question about how we measure the CMB. Come to that one in a bit. But yeah, so when we see the variations of visible light, that's a big variation. But when we're talking about these tiny, tiny, tiny fluctuations on the CMB, they are tiny, tiny fluctuations within the microwave range of the electromagnetic spectrum. They are really, really small. So substantially smaller than the whole range of the visible spectrum of light, if that was the question. And hello, Matteo, great to see you here. Unusual to see you in the comments, but very nice to see you. And I will get to that question soon. But going back to the other questions here, there was a question, okay, from James. You said we can decrease speed of light, for an example, putting it through a medium. After it comes out of the medium, though, does it remain slower or does it increase back to normal speed of light? That is an excellent question. Light will always travel at the speed of light in a vacuum. If it's traveling through the emptiness of space, it will always travel at the same speed of light. When it travels through a medium, it slows down. But this is not in an offense. Like, we have the idea that if you slow down a train, then it needs to accelerate again to speed up. This is not true for the speed of light. It's not like a slowing down and an accelerating. It's more like it's traveling through something that is making it harder for it to travel. And once it's out the other side again, it can recover the initial speed. So when a photon, a particle of light, is moving in a vacuum, it will always travel at the speed of light. Once it enters a medium, for an example, water, it's going to travel slightly slower. Through air, it's going to travel slightly slower. Once it clears that medium, it's going to go back to traveling at the speed of light in that in the vacuum or in whatever it's in. So we can decrease the speed of light somewhat by putting it through water or through air. It slows down, but then it speeds up back to the speed of light once it's out. So it doesn't remain slow. You can't then say, like, I've slowed it down enough that now when it goes back into the vacuum, it's going to still be slow, because there's nothing there that's hindering it from traveling properly. So it can travel at the normal speed. It's like if you try to move through treacle, it's going to be quite hard. You know, you're going to have to move through treacle. You'll probably get very sticky, so it's probably not advisable. But when you come out of the treacle, you can go back to walking normally. So you only slow it down momentarily, not yeah, typical science is, what does this button do? I found a button, I had to press the button. Yeah, so you slow down like momentarily, but not constantly. Once it's back in the medium, it will be back at the speed relative to that medium. So you don't slow it down permanently. Same as if you were walking through treacle, you'd slow down while you're in the treacle, and then you'd be back to your normal speed outside, although you'd probably want to stop and have a shower after that. I did watch the video of the microwave ants. We discussed that at the beginning, Scott. Yeah, it's a very cool topic. Microwave ants, very fun. Very fun things to learn about. Okay, so where were my questions? I'm quite behind with the questions now. I'm answering questions that came in 11 minutes ago, so I'm a bit behind with the questions now. As always, I will try to catch up by the end. Okay, question from Paul. If from an outside observer's point of view, nothing ever finishes falling into a black hole, does that mean from an outside point of view that a black hole never finishes forming? Oh, that is a big question there, Paul. That is a very cool question. So there's a new heart button appeared on the YouTube app. Yes, everyone, if you see this heart button underneath my stream, please do press it. Or if you see a thumbs up, please do press it. It really does help with engagement. Press all the buttons. Please don't press the thumbs down one. Press all of the other buttons, see what happens. If in doubt, just press buttons. Cool stuff happens usually when you press buttons. Also, I relearned recently that I should absolutely not be trusted in a room with a big red button on the wall, because I absolutely will press it, even if there's a sign, especially if there's a sign saying do not press. Anyway, do not leave me unsupervised around big buttons, because I will press them. So, does a black hole ever finish forming from an outside point of view? Now, the reason from an outsider, if you throw an object into a black hole, you'll never see that object fall into the black hole, because from your perspective, they're going to slow down so much, they're going to be trapped on the event horizon. From their perspective, they're not going to notice that they're slowing down. However, this happens because the gravitational force is so big that nothing can escape, not even light, nor information. So once you reach this event horizon, you will never see an object falling beyond the event horizon, because that information will never be able to reach you. However, when the black hole itself collapses, when the black hole forms, at that point, it is not yet it doesn't yet have a big enough gravitational presence to stop everything from escaping. So until the point where you have the black hole, once it's forming, you can still see this happening, obviously with some distortion. And the way most black holes are formed, if we think about stellar black holes, is when the star reaches the end of its lifetime, it can explode as a supernova, and the core that's left behind collapses. It's like a star is a constant battle between pressure going outwards and gravity going inwards. As a star reaches the end of its lifetime, it can expand, collapse, goes through this kind of like pulsating period. And then at some point, it will push out all of its outer layers in a supernova, and what's left suddenly has none of the pressure, so it can go in gravitationally and collapse and form the black hole. Now, at this point, stuff can still escape. You see the big supernova, but then the remnant itself is something that you can no longer see, because to see this core that has now become the black hole, you would need to get information from beyond the event horizon, and this can't happen because it would need to travel faster than light. So this means that we can see a black hole form in the sense that we can see the supernova, and then we can measure objects close by to see if the remnant was actually a black hole. So at that point, that's something that you can still see, but you cannot actually see the black hole itself, because a black hole by definition is not emitting any light. So even though objects do get trapped on the event horizon of a black hole, this is true, but the formation part of a black hole, at that point, stuff can still get out. For an example, the outer layers of the star get out in the supernova, and then the rest collapses to form a black hole. But that is an excellent question, and one that my answer might have been a bit too hand-wavy for. So if what I said is not clear, or if anyone here disagrees with what I said, I know we have at least one physicist in the audience. So if you disagree with what I'm saying, please do let me know in the comments, and we can try to go through it again. If what I said is not clear, also let me know, and we'll go through it again. But it's very fun to think about the stuff being stuck on the event horizon and how that happens and what's happening there. Follow-up thoughts. I will go back to the questions. I just try to do the follow-ups as and when they come. When I detect a gravitational wave, I am seeing an object, the neutron star to the other black hole, falling into another black hole. Yes, so the neutron star or the other black hole, yes. So in a way, you are not seeing the object itself, you're noticing the effect of these objects falling. So when two black holes smash together, they start to collide, they start to dance around each other, they gradually get closer and closer, and at some point they crash together, they collide. This whole cycling around each other produces gravitational waves. In fact, the way that the orbit decays, so they get closer and closer by letting off energy, and that energy is carried away by the gravitational waves. The gravitational waves carrying away the energy is what causes them to get closer and closer, and vice versa there. So what you're actually seeing with the gravitational waves is the gravitational effect of these objects coming together and smashing together. But if you were there at the time trying to look at this, obviously you can't actually see two black holes. But let's say you have two neutron stars, which are stars that are really so dense that you can fuse protons and electrons together to make neutrons. So if you could see two neutron stars, those watching them collide would be very interesting, because from your perspective, there will be gravitational effects. You would probably, if depending how close you are, you might never actually see them come together. But from an outside, the gravitational waves are still going to be emitted. So when we're looking at gravitational waves here on Earth, these are events that have happened really, really, really far away. Neutron stars or black holes have come together, and what you're seeing is the gravitational effects after this. We've also been able to see things like black holes eating up planets. There was one quite recently where there was like not really a planet, I think it was a nebula or some small system that was thrown around a black hole and gradually torn apart. And this was something you could see. And you see this all gradually get closer to the event horizon, but never actually fall in. There is a fun question of what happens to the event horizon. So the event horizon is the point of no return. So there is a question of what happens when you have two black holes coming together. How do you describe this event horizon? Is there a point where they just merge? Is it gradual? And this is something that is really difficult to understand and to simulate, because the event horizons are very difficult to model. And there's a lot of people doing very cool simulations of what happens exactly to the event horizons of the two black holes as they come together. Do you end up with like a ring event horizon? You can. Do you end up with a naked singularity, which is a singularity that has no event horizon? It's very weird, and this is why you need to do general relativity simulations, which is very difficult. But long-winded answer there. The conclusion of what I'm saying is, if two black holes smash together or two neutron stars smash together, they do produce gravitational waves while they are in spiraling, and when they collide, and then it stops, because once they've collided, there's no longer this acceleration that is producing the gravitational waves. At that point, if you then jump into a black hole, or you throw your friend into a black hole, you will never see them past the event horizon. Hope that makes sense. Black holes are a very confusing topic, and one that is better when my mind is actually in it. And today, these are very difficult questions to answer, but very fun questions. 3 in a row, no worries, Paul. You're always allowed to ask questions, and I'm answering the ones that are connected, and then we'll go to the other ones. Does the gravitational wave energy come from the potential energy of their orbits decaying, or does it come from the mass of the black holes? I'm not going to be able to solve those equations in my brain. Let me just think about that. So for the first detected events, as we're seeing here in the comments, there was a 135 solar mass black hole, 130 mass solar mass black hole. They smashed together. They left behind a remnant of 62 solar masses. So 3 solar masses were converted into gravitational waves. But those solar masses, were they directly from the mass or the potential of them in spiraling? I'm going to say from the mass, because as the numbers add up, we do carry away 3 solar masses of energy in the form of gravitational waves. But when you pull out the full equations and which terms you get that from, I'm not going to be able to do that off the top of my head or back of the envelope calculation. Would need to be much more awake than I am for that. Hope that answered all of your questions, Paul. And if not, we can carry on with gravitational waves, because it's a very fun topic. Okay. It comes from okay. Yes, thank you. So Matteo is just adding the clarification here. It comes from the conservation of energy, which everything does in the universe. Angular momentum turns into the gravitational wave. So as they're coming together, because they're getting closer, the angular momentum is kind of decreasing. So they emit more gravitational waves. As they get closer and closer, you need to compensate more energy loss, so you get more and more gravitational waves. So it's not from the potential energy, it's from conservation of energy, which is always the case, but from the angular momentum. Just in general, believe what Matteo says here in the comments. And if anyone doesn't know who Matteo is, he was here on the stream twice, many times actually, on on Cup of Cosmology only once, but you all know Matteo. He's been on the stream before. We have papers together. Okay, going back to the other questions before we get too caught up in black holes. It's hard to escape once you start on black holes. Question from David here. What disproven cosmological theory do you really wish was true? Well, that's a very cool question. I like theories that get disproven or models that get disproven because that's how we progress science. You know, you have some idea, you throw it out, you move on to the next one. I think a big bounce would have been a bounce and a big crunch would have been very interesting. So we know that the universe is expanding and this expansion is actually accelerating. But people used to think that at some point the expansion would stop, whatever would fuel this initial expansion will kind of run out, and then the gravitational force will pull everything inwards, and at some point the whole universe will collapse upon itself. Now that would have been a very, very cool idea, because then instead of seeing galaxies move away from you, things would suddenly start rushing towards you closer and closer and closer, and like the whole universe would be falling on top of you. Which sounds fun and terrifying, but also fun, like the universe collapsing around you. But we know that the universe is expanding and this expansion is actually accelerating. So it is expanding faster today than it did in the past. This means that this idea of the collapse is unlikely to happen. The big crunch is less likely now because it seems like not only stuff going away, it's going away faster and faster. Our best leading idea for why this is happening is the dark energy. Now, dark energy is one of the three components that makes up the universe. Everything we know about the universe, there are three components. Everything you see, everything from me, my tea mug, the stars you see in the night sky, this is normal matter. Normal matter accounts for 5% of the energy budget of the universe. There's 26% in the form of dark matter. Dark matter is this weird type of matter that is driving the accelerated expansion of the universe. Dark matter is this weird type of matter that interacts gravitationally but doesn't interact electromagnetically. So it's kind of this invisible matter that you don't see. And then we have dark energy, which is driving the accelerated expansion of the universe and accounts for 69% of the energy budget. So this dark energy is what is driving the accelerated expansion of the universe, we believe, but we have no idea what dark energy is. We're still trying to figure that one out. But thanks to dark energy, it's quite unlikely that we're going to have a big crunch. So to the question of what cosmological theory did I like that is now disproven, I think I would go for the big crunch, just because it would be very fun to have the whole universe collapse upon itself around us. I think that would be a pretty fun scenario, just have everything falling upon itself. Terrifying, but fun scenario. Okay, going back through the questions, I answered the CMB ones, answered those. Answered that one already, okay. Then there's another question here about particle physics. Okay, before we get on to that, what if the dark energy decayed tomorrow? What would happen to the universe? Would we see it on human timescales? Love these hypothetical questions. So let's say dark energy disappears tomorrow. First, we need to ask, how does this happen? Is it an instantaneous process? Is it a slow process? For the sake of discussion, let's say that dark energy just disappears tomorrow. Dark energy decays into something. What it decays into? You know, let's make it easier. Dark energy decays into the standard model particles. You suddenly just have a lot more light in the universe. What would happen to the universe? Well, if you suddenly kind of run out of dark energy, the universe would stop expanding. Would this be instantaneous? That depends how quickly the dark energy disappears. So the heart button makes a little heart float up on the screen. Do you see that? I do not see that, but it might be because I'm on Restream and not directly on YouTube, and maybe if I was on YouTube, I would see the hearts. That would be very cool. But I like the Periscope hearts, but I don't see them here. At least I didn't see any hearts pop up, but do feel free to click again and see if anything happened, but I did not see any heart appear on my screen. So if the dark energy I guess the slowing down of the expansion of the universe would be proportional to how quickly dark energy disappears. But if there's nothing driving the accelerated expansion, dark energy has decayed, so there's nothing driving the accelerated expansion anymore, this expansion would stop. And eventually the gravitational force would take over and would pull everything inward. I don't think this is something that will be noticeable on human timescales because the universe is so ridiculously big right now. Everything is so very spread out that it would take a while, I think, for the gravitational force to pull things in. Now, we know that the closer things are, the more gravitational force they feel. So, like, Andromeda is already, the closest galaxy to us is already falling onto us. Other galaxies in our local group, we might start to see them fall on us, but I don't think that's something perceivable within human timescales. So, let's say we switch off dark energy, depending how dark energy switches off, you would have a more or less gradual slowing down of the accelerated expansion of the universe, and eventually this could turn around and collapse back upon itself. But all of this is very hypothetical, and I'm thinking on the spot here, so this may or may not be accurate, but it would be cool. We don't have any reason to believe that dark energy is going to just switch off tomorrow, but we also don't really know what dark energy is. So we don't know what started dark energy, if it was like an early dark energy, a new dark energy. So it could, if dark energy suddenly decayed, maybe dark energy decays into dark matter to make things more fun. It could be fun. There could be a lot of cool stuff happening. But I'm not sure if we would see it on our human timescales. It would very much depend on how quickly things decay, I believe. But Matteo, as you asked that question, if you have different opinions there, do let us know. Sticking on the topic of expanding universe, I wonder if the expanding matter in the universe has momentum from the expansion, or if it is just space expanding. If just space expanding, then without dark energy, it would all stop. Yeah, so we generally consider that it is space-time itself that is expanding, not objects gaining random velocity. Like, they're not being kicked in that direction. They're kind of moving with the accelerated, with space-time. So all the space is expanding, and therefore everything is expanding as well. Of course, galaxies do have their own motion. We are part of a local flow that is moving in a specific direction. But I think if you turn off dark energy, you're turning off the expansion of space-time itself. And this isn't really giving things momentum that they would then need to gradually slow down. I think if you gradually stop the expanding of space-time, then things would gradually stop moving away from each other. If you turn it off suddenly, like, okay, that's it, no more dark energy, which seems quite implausible, but let's say for fun that we do that, I think there wouldn't be enough momentum on things that they would carry on. If dark energy stops pushing things away, the gravitational force would gradually take over. But I think that would be a slow and gradual process. Okay, quick question. What's the map in the background? That is just a standard world map, but this is a human-centric one, so it is not using the standard flat hammer. It's not using the standard projection. It's using a Mercator projection, which makes countries more accurately depicted, and it's focused on humanity. So this is a Kurzgesagt map from Kurzgesagt, the YouTube channel that puts out amazing videos, second best science communication YouTube channel out there. Obviously mine is the best. And it's centered on, like, where are the 10 most populated cities, and you can see each glowing dot here represents a specific, like, 1 million people living there. So it shows you where humans are, and like where's the most populated area, where's the least populated area. It's a very cool map. It's from Kurzgesagt, and I like Kurzgesagt stuff. So there it is. Would the universe itself have a momentum? Let's say the dark energy disappeared. Would the universe instantly react? I guess you could put that question directly into the equations and see what would happen. I think the universe itself, like, I would say that space-time itself does not acquire momentum, right? It's not like, no, I don't think space-time itself acquires momentum. If we think about how we put stuff into the Einstein equations, we usually have curvature on one side and, like, energy on the other. So I would say that while they are connected, I don't think space-time itself gains momentum from the dark energy. So if the dark energy disappeared, I think the universe would, or the space-time metric itself would feel this instantaneously. I don't think the metric will keep on going. But it might depend on how dark, so it will depend on how dark energy couples to the metric. and like the metric being the curvature of space-time, basically. And I'm not sure off the top of my head how dark energy couples to the metric of space-time. I feel like this is a conversation to be had over beers one evening, or maybe with a notebook where we can draw these equations. But yes, I would say dark energy doesn't couple too much to the metric, so that if dark energy turns off, I would say the universe would feel like as dark energy turns off. Yeah, this also correlates with the light pollution map. That is very much not surprising, given where you have people, you have more light. And I agree that maps, geography, and cartography is great. I actually love maps. I have a folder of bookmarks for random maps that I find. If you ever find random maps that you think this is bizarre, please do send them to me. I love random maps. Like any random map that you find, I'm happy to see it. There's a map that combines several things I like trains and maps, and it shows you how far you can get within a given country if you're traveling by train. And you set how many hours, and then it's like, if I want to travel 3 hours and I start in this city, how far can I go? And if I want to travel 5 hours and I start in this city, how far can I go? It's so cool. Anyway, please do feel free to send me random maps that you encounter. Okay. Now, before I get completely baffled by dark energy coupling to the metric, I'm going to go look at steroid equations after this, because now I'm confused by how dark energy couples to the space-time metric. Going back to the questions, there was another question I wanted to answer that came in 23 minutes ago. I'm very behind with the questions because we went on fun topics here. Since we found only the simplest version of Higgs postulated at the LHC, why do we believe higher energy in LHC will unlock new particles? For an example, supersymmetry. So supersymmetry is this idea that every particle has a symmetrical partner. Like you can have a top particle, and then you can have an S-top, which is the supersymmetrical partner of the top. So you go from top to stop. We're great at naming things. Now, SUSY was very nice because it ties nicely into string theory. However, we have not yet found any evidence for SUSY, for supersymmetry, at the Large Hadron Collider, and many people thought we would. Moving from a Large Hadron Collider to, for an example, the Future Circular Collider isn't just about looking for SUSY, although that is one thing. It is not the main goal. It's really to push the energy levels to understand what happened in the very early universe, to push it to the point where the force is separated, to see what was happening at these timescales. A lot of people these days don't. I feel like SUSY has lost a bit of popularity compared to when I started my undergrad, where everyone's like, SUSY's around the corner, we're going to find supersymmetry. But there's still a lot of new stuff we could potentially find if we go to higher energies. There is always a question of, is it worth investing a lot of money to go to new energies to find hypothetical things? Like, we know that the standard model is pretty good, but there's a lot of stuff we don't understand. And going to higher energies might help us learn more about dark matter. We might find new random particles that we didn't expect. We might find new properties that we didn't expect. But not everyone in the community is happy with the idea of going to higher energies, because some people think we're done. But for an example, we don't yet know how neutrino masses work. Where did neutrinos get mass? Going to a Future Circular Collider could potentially help us uncover this by uncovering new particles. So it's not just about looking for SUSY, which may or may not be out of interest depending on who you ask, but it's looking for everything else that we might be able to find in a future collider. So there's a lot of things that we can hope to do, but there is a debate in the field of, is this the wise place to throw our money? But the general consensus is that, yeah, this does seem like a good idea because we might find stuff. So not necessarily SUSY, but hopefully we will find some cool stuff if we go to a Future Circular Collider. So in any case, I think it's cool. And the more experiments we do, the more likely we are to find stuff. But I could see why some people weren't so keen, given that we found the Higgs. Some people might not be so keen on going to a bigger collider. But usually when we do physics experiments, we find lots of cool stuff. So I think it could be fun to do. Personally, I'm not a fan of supersymmetry. I feel like when I started my undergrad, I was a fan. I was sold. Like when I started studying physics, everyone was talking about supersymmetry. It's like, wow, this is amazing. And the more time has gone by where we haven't found it, the less motivated I am by SUSY. But some people still believe in SUSY, in supersymmetry. Okay, Then there was the question by Matteo that I'm still thinking about and I'm not going to answer. How could we measure these tiny, tiny temperature fluctuations of the CMB? And for that, I would tell you to ask an experimental physicist. But basically, what we had to do is we had to send a satellite to space. So in order to measure these tiny, 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 tiny differences in the CMB, like this fraction of a degree Kelvin, in order to measure these differences, we had to go to space. So this image here was obtained by the Planck satellite. The Planck satellite was sent to one of the Lagrange points, Lagrange 2, where it is very shielded from sun. It was very shielded from a lot of stars. It's kind of hiding in the Earth's shadow in a nice gravitational balance point. And it is something that was a huge engineering feat. It took many years to build Planck, to launch it, to get the data. Planck took data between 2009 and 2013. It took over 5 years to analyze the data and get this. But so it's a very incredible experiment that was really technologically incredible. As to how the technology works to measure these tiny, 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 tiny differences, I'm not an experimentalist. I'm not sure. I've read about it multiple times, but right now I can't completely remember how you measure these tiny, tiny, tiny temperature differences. But I do know you need to go to space and you need to take care of all of the things like galaxies in front and all of the stars that could get in the way. So you need to subtract a lot of things to get this map. But at the end, you do manage to get this. And indeed, the ants, to avoid being microwaved, the ants should stand in the blue parts of the CMB. We should let the ants know to head for the blue parts of the CMB. I feel like this ant conversation is getting very meta now. Okay, so do you wish the Susie was one hypothesis that was true? Honestly, not really, because I'm not really a fan of string theory. I think it's something that mathematically is very nice, but it also doesn't really apply to our universe as far as we know, because you need a lot more dimensions to explain it. Susie would have been nice in that it would have made progress in that regard, but I also think it's fun that that's not working. I don't know. I think it makes it more interesting. So I'm very much not disappointed that Susie wasn't. Or maybe someday we will find supersymmetric particles, but it's not on my wish list. I'd much rather figure out neutrino masses or measure spectral distortions before finding Susie or string theory in general. So that's something that's like, yeah, it's sad for people who worked on it, but it's cool. It's cool. Good stuff. Okay, sticking on particle colliders, there was a question quite some time ago by now. Why do accelerators need to get larger to reach higher energies? Why isn't it possible to increase energy without making the accelerator larger? That is a great question. So the way you accelerate particles in a collider is by using magnets. So the Large Hadron Collider is a circular ring that has super-cooled magnets around it. So the particles moving through this are going to be deflected by the magnetic line. So you're going to create a magnetic field that is going to accelerate the particles. But then you're limited by the strength of the magnets. And you're limited by the volume of the magnets that you can put around this specific area, or the size of the magnets. So with the Large Hadron Collider as it is, you can put these ring of magnets around 27 kilometers of tunnels. And you can accelerate these particles to about 99.9999% the speed of light. So you can get them very, very, very close. But in order to get them faster, you need more powerful magnetic field that you can't get given the size of the magnets that you have and some technological limitations. You also need a bigger curvature radius in order to get it to go around more and more and to be able to kind of use conservation of angular momentum to flip that around a bit faster. So in order to really scale up the speed at which they spin, you need to get a bigger tunnel. So you can't just like add more voltage to your machine. You really need a bigger machine so that then it can accelerate. Already at the Large Hadron Collider, the particles go through several different smaller circuits where they do like a pre-acceleration before they're injected into the big tunnel. And then they loop around multiple times, getting faster and faster until they reach the kind of maximum that you can reach there, and then they're brought together to collide. So going to a future circular collider, the LHC would be the pre-acceleration, and then they would be injected into the bigger one, where they have a bigger radius, bigger magnets, and then they can accelerate more. This is, again, coming from someone who does not work on experiment on designing the experiments. This is just a general idea of how things go. Hey, David Dunn, nice to see you here. Great to have you come in as well. I just saw that you came in. And Savant, great to see you as well. Nice to have all the regulars here. It's always nice to see people coming back time and time again. I know some of you have been here for like 7 years now. Still impressed that you keep coming back. 7.5 years by now. Okay, so going back to questions. Yes, typical scientist, what does this button do? Yes, I found a random button. So that's how far back I am in the comments, by the way. Let's see, more questions. We did gravitational waves. We did those. We talked about dark energy decaying. We talked about that. We talked about the map in the background. Okay, just jumped a bunch of comments because we already addressed those. Among dark matter candidates, which are your favorite particles? Axions, or neutrinos, something else? That is a great question. And my answer to that question changes every time I get asked. So we don't know what dark matter is. We're pretty good at figuring out what dark matter isn't, but we haven't yet figured out what dark matter is. Sterile neutrinos are a nice option. So neutrinos are a type of particle that is part of the standard model of particle physics. They're really, 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 really small, but not quite massless. So they do have a small mass, which means they don't travel at the speed of light. There are 3 flavors of neutrinos. We call them the electron neutrino, the muon neutrino, and the tau neutrino. And neutrinos have the cool things that they can change. They might be emitted as an electron neutrino, but by the sun, for example, and by the time it reaches us, it might be a muon neutrino. So this is very cool. They have this oscillation. But we know of 3 neutrinos, and particles all have a chirality, which means a way they're pointing. You can think of this as your hand. We have a left and right hand, and if I put them together, they're quite clearly not the same. They have right-handed and left-handed. You would need to flip one in order to align them. So a lot of things in the universe also have a chirality, like DNA has a chirality, specific direction. Neutrinos do as well. So neutrinos are all left-handed. We don't know why, but neutrinos are all left-handed. Now, there could be a 4th neutrino, which would be right-handed, and this is what we call a sterile neutrino. Sterile because it can't interact with the other ones. And sterile neutrinos are a possible dark matter candidate. Now, it's one that is quite interesting because we would already know how it behaves. Like, we know neutrinos. Neutrinos are a thing we have. So from there, getting a different type of neutrino as dark matter seems quite realistic almost. However, we don't have any clear signs that sterile neutrinos are the way to go. The sterile neutrinos would affect some things in the universe, like how galaxies are distributed, like what we call the Lyman alpha spectrum, and there's not clear evidence anywhere for sterile neutrinos. I think it's fun, but to me it also feels kind of like a cop-out, like instead of finding a new particle, it's like, oh, let's just add another type of neutrino, and not as fun for me. Axions is another type of dark matter candidate that is very interesting, but also kind of boring. Axions can do a few things. They would solve some early universe problems. They have the fun thing that they can make light travel through a wall, and we look for them by trying to shine a light through a wall, and if it happens, you might find an axion. It's very cool. So I think axions are fun. We might find them someday. Primordial black holes are another dark matter candidate that I think is really cool, where you could have black holes formed in the very early universe, and these could be dark matter. But I actually think dark matter is going to be something that we haven't thought of yet. I'm ridiculously optimistic that A, we're going to find dark matter, B, we're going to know that we found dark matter, and C, it's going to be something that we have not predicted yet. It's going to be something random. There are some people working on things like dark atoms, which is very cool. If you could have atoms made of dark matter, I think that's very cool. So I think my favorite dark matter candidate depends on which day you ask me, but I will never say WIMPs, like weakly interacting massive particles. Those are the standard vanilla dark matter. That's very boring. So I think it will be something different. Maybe something like a particle that has cannibalism, or a particle that bumps it, or 3 different particles that react in a different way. But yeah, depends on the day, but I don't think sterile neutrinos for me, personally. When you say neutrinos oscillate, it makes me think it is regular electron to muon to tau and round again with a fixed interval between each change. Is that right? Not completely. So there's different probabilities. So if you start as an electron neutrino, there are different probabilities of going to muon or going to tau. And the jump between electron and muon and electron to tau neutrinos, the muon one is easier because of the well, it is not so easy to go down that path because there are the 3 flavors. But when you talk about the oscillations, you actually have to go to like 3 different masses, and you don't have 1 mass per flavor. You have like 3 mass states and 3 flavor states, and they're entwined. So I think it is more likely for an electron neutrino to go to a muon neutrino than a tau neutrino, but it doesn't have to follow this ordering. It can go from one to the other and back and forth. So it can start as one thing, become another thing, can start as an electron neutrino, those are the easiest to produce, and it could become something else. So the way it changes between those three is related to the separation of masses between the three types of neutrino. And then you have three masses, three flavors, and there's some mixing. So it's not easy to describe, but it doesn't have to be going in this fixed direction of electron, muon, tau, electron, muon, tau. It can go in different directions and back and forth. You can go from electron to tau, from tau to electron, back and forth. So there are different paths. Not many, because there's only three things. There's not that many combinations you can do. There's only three different pathways there, but 6 different pathways. But you can take any of them. Yeah, 6 possible pathways. You can take any direction. Okay, going back to the questions here. So my favorite dark matter candidate depends on the day, depends on my mood. But often I might say axions or sterile neutrinos. I will sometimes primordial black holes, but I think it's going to be something different. I think it's going to be something new and weird and crazy. And, maybe we never find dark matter, but I hope we do. Or maybe we're all wrong and there is no dark matter and we just need to modify how we use Newtonian's gravity. However, then we can't explain the CMB. But maybe we'll find something at some point that surprises us all. My tea is so cold at this point, but I have to use it up. Okay. Question about Hawking evaporation. Nice question when we've got 5 minutes to go. So Hawking evaporation is this idea that if you have a black hole on the event horizon of the black hole, you can produce a particle and an antiparticle. The vacuum of space does this often. Usually they evaporate and nothing happens. But if this happens on the event horizon of a black hole, one particle can fall in, one can go out, and suddenly you've created a particle from nothing, which means that the black hole is going to lose mass to compensate for the escaping particle. So the question, if the dissipation is happening only from the event horizon, why would the whole black hole dissipate? Matter energy can't come from within the black hole. Excellent question here. So if you're producing particle-antiparticle pairs on the event horizon, then you're borrowing energy from the universe to produce these. And to give it back, the black hole will lose mass. Now, this is kind of a roundabout way of saying that the black hole is emitting a particle, because the black hole cannot emit a particle by definition. So they're created, you kind of borrow energy from the black hole to create the particles, and then one escapes, one falls in. Now, how could this then cause the whole black hole to evaporate? Here we get into the information paradox and holography. So can a black hole fully be described by its surface? Some people think yes, and this idea of describing a whole 3-dimensional object by its 2-dimensional surface is what holography is. And if a black hole can be described entirely by its surface, then having Hawking evaporation happening on the surface of the black hole is enough to kind of carry away mass from the whole black hole. Then what happens to the information contained in the black hole if it actually does evaporate? That's known as the information paradox. And these are questions that require a whole stream and are not easy to answer. And we get really into trying to unite the gravitational world to explain black holes and the quantum world to explain Hawking radiation. So if you're confused by Hawking radiation, don't worry. Almost everyone is. It's a very confusing topic, and it's one that you really need to think about a lot. And there's still so many open questions there. But if you consider a black hole to be described entirely by its surface in a holographic approach, which a lot of people do consider it, then stuff that's happening at the event horizon, which is quote unquote the surface of the black hole. I can't believe I just did the quote unquote. I always hate it when people do that. Okay, so the so-called surface of the black hole, the event horizon, can really describe the whole black hole. So then stuff happening there is as if it's happening to the whole thing. But for this, we really get into like quantum gravity, and it's not an easy topic, and especially not when I have like 5 minutes of the stream left. It is a great question. Maybe we can go into that a bit more another time. But for now, it's yes, Hawking radiation is confusing. Okay. Then going back through the comments here, we got distracted by maps. Maps are cool. Maps like that travel one are used in competition policy analysis for things like supermarket mergers. That is cool. I'm not surprised, but maps are cool in general. Had a few people coming in late, so do you wish to be covered, Susie? Okay. Question here about neutrino. Any progress on the neutrino background radiation detection in the past couple of years? Have we started looking for this low energy neutrinos? Yeah, that was indeed part of my thesis defense. Thank you for the question and thank you for reminding me of that. So, yeah, let's hope it's not a sterile neutrino. I agree. It would, yeah. I realize that's a reply to the previous comment. So we have the comment here. My love life is like dark matter. It theoretically exists. And Matteo added the comment of let's hope it's not like a sterile neutrino. And I am very amused at that string of comments. And I see the comment by David Dunn of cold dark tea particles. Exactly. My tea is like dark matter, except I can actually drink it. Okay. So in the same way that we have the cosmic microwave background, this background that we have at the background in the universe, this is when photons, particles of light broke away from everything else. But much earlier than this, there could have been a time when, well, there was a time when neutrinos did the same. Neutrinos in the very early universe, a few seconds, like 10 seconds after the end of inflation, neutrinos broke away as well. This is called the neutrino decoupling. This means that these early universe neutrinos are traveling freely throughout the universe. And in the same way that we have the cosmic microwave background radiation of photons or particles of light, there is quite likely to be one of neutrinos as well. And if we could ever measure this cosmic neutrino background, we would be able to shift our, so the CMB, the cosmic microwave background, is a snapshot of the universe 380,000 years after the end of inflation. Measuring the cosmic neutrino background would push us to 10 seconds after the end of inflation. It would be pushing our understanding of the universe back so close to the end of inflation, just like 10, 20 seconds afterwards, approximately. So that would be really, really, really cool. And it's something that is going to be very, very, very difficult because neutrinos zip through you without interacting. Measuring neutrinos is always very hard. Measuring these low energy neutrinos at the background of everything in the universe, it's going to be very difficult. But there are experiments trying to do this. Ptolemy is one. I'm not sure when Ptolemy is going to launch, but Ptolemy is an experiment that is hoping to measure this cosmic neutrino background. And I'm not sure when it's going to launch. And Google is not helping me. Let me just check that again. I'm just asking Google when it's going to launch. So I think it's not even been, I'm not sure if it's been funded yet, but it is something that people are hoping to launch in the future. And I'm not finding a possible launch date. I'm finding a lot of papers saying, like, we want to do this. This is something we should do. But I'm not sure when that might happen. But it's, it's going to be something that is going to be very, very, very difficult to measure. And it's something that we haven't made progress on yet. You know, if we ever measure it, I am very likely to start the stream with, we have found the cosmic neutrino background, because it would be an amazing day. But there are plans to do it someday, potentially, because it would be really, really cool. It's a question of whether we can get rid of all of the other noises, if we can actually do it, if we can actually measure it. I hope someday we do launch an experiment to look for the cosmic neutrino background. It would be very cool, but I'm not sure if we'll ever be able to do it. So to the question of, is there any progress? None yet. But hopefully someday we might get there. Okay, follow up on neutrino mass, trying to understand if this is different from other particles. Aren't their mass imputed by their interaction with Higgs field like others? Yeah, so left-handed neutrinos do get their mass from the Higgs field, we think, but also because they're left-handed, they don't couple to the Higgs field in the same way that other things do. So the Higgs particle is what gives everything else mass in the universe. It's the boson. It's the one that gives everything mass. It gives itself mass as well. But neutrinos and Higgs are quite hard to put together. And then there's the thing of how massive neutrinos are, how they got their mass, what's the difference? But like, do you have two light neutrinos and one heavy one, or two heavy ones and one light one? This is called the mass splitting. And these are open questions. So neutrinos don't gain their mass through Higgs interactions like everything else, because they're left-handed and they're quite hard to put together with the Higgs field. To answer that question, you need to pull out the standard model of particle physics and unpack the equations. But we haven't yet measured the cosmic neutrino background. We're hoping to. We don't know how neutrinos got mass. We're hoping to figure that out one day as well. Excellent questions, all of these. I love the neutrino questions. I feel like we have some very difficult questions today, and I love all these questions. Question from David Dunn. How are you today? Thank you for asking. I am very tired and kind of distracted, but I am doing well and happy to be here chatting to all of you, especially with all of these such fun questions. Okay, gonna zip through the questions now because it have been online almost an hour, actually over an hour now. So I'm amused at all of the comments coming in of people comparing their love life to dark matter to dark energy. You know, how I'm having fun with these comments. So where was I? Yeah, I'm going to zip through the questions that I haven't answered yet because I am at 1 hour and I'm almost caught up with questions. Does lead have a refractive index? Given that gamma rays can pass through lead just like light through glass, gamma rays should undergo refraction just like visible light. So the refraction index tells you how much something slows down in a medium. So how much light slows down in a medium. So the larger the refractive index, as more light slows down. It's basically being deflected. So instead of traveling in a straight line, it's traveling along a bumpy path. So that's why it takes a bit longer to travel through the thing. So through lead should have, I believe everything has a refractive index. I think lead also has a refractive index, and I believe it's a very, very, very high refractive index. So I'm just asking Google refractive index of lead. I like doing this live because then you will see what we actually do as scientists when we don't know something. Like there's this idea that scientists know everything, and it's not true. As soon as I don't know something, I ask Google, and then Google usually tells me the answer. So yes, lead definitely does have a refractive index. According to Google, ordinary glass has a refractive index of about 1.5. If you have glass with lead in it, so leaded glass, that pushes it up to 1.7, that is lead glass. As for lead itself, what is the index of refraction of lead? I'm not getting an answer for lead itself, I'm getting an answer for lead glass. But yes, it should have a refractive index of about 5, apparently. Yes. The refractive index of lead is around 5, I believe, yes. So lead also does have a refractive index. That means it's going to slow down light. Every material would have a refractive index. As light travels through it, it gets slower. The higher the refractive index, the more something slows down. So yes, lead does have a refractive index now we know. But I do like Googling things live. Also, I can always Google and answer questions as well. But it's always fun because then you see how we actually go about doing stuff. Because when I don't know something, my first approach is to Google. My second is to go find another physicist who might know things. Because usually, if I don't know something, somebody else might, and that's how we get to do stuff. Is it fair to imagine light doesn't slow down at all in medium, but just travels at full speed on a zigzag path? I'm going to say yes to that question, that instead of traveling in a completely straight line, it bumps about a bit. I'm going to say yes, but citation needed. So yes, put a yes asterisk to that question. High school physics taught me diamond has the highest refractive index of 2.4. I guess that's the highest refractive index of a material that is still transparent, because of course lead doesn't let light through unless you have very, very high gamma rays or stuff like that. So yeah, I think the diamond has a very high refractive index. That's why light goes in and shoots out in every direction and makes very pretty stuff. For optical light, thank you. Thank you for that clarification, David Dunn. Yes, so diamond has the highest refractive index for optical light, so that's light of a specific frequency or specific wavelength, which is the light we can see. But then, of course, if you're talking about gamma rays, then it changes on depending on different. So the refractive index is going to be the same, but the light that can pass through is different. Okay, more questions. Let's see. I think I almost got to all of them. I will get to all questions before we go. This is how you keep me online. Keep the questions coming, and I will try to answer all of them. We did neutrino oscillations. Your brain remembered saying math is Markov chain. Yeah, there's always Markov chain. Yes. Neutrino oscillations is not mediated by force carrying particles. Is it correct to say we don't understand how they oscillate? Yes. Neutrino oscillations is one of those things that we can mathematically describe, like we know the probability of this, But we can go down to like, okay, you have these mass mixings and you have the flavor mixings and they mix together and this is what happens and you can calculate it very precisely. But until we understand exactly the neutrino mass, understanding the neutrino oscillation is the next thing. I am zipping through these questions. Okay, cold dark T particles. Yes, my love life is like dark matter. It theoretically exists. Let's hope it's not sterile neutrinos. My love life is like dark energy. It keeps pushing everything away. I love those questions. Likely to remain a constant. Yes. So, have I been to Estonia yet? I have not been to Estonia, and I need to because it's literally just a boat trip away, and the boat doesn't take that long, and it's not too expensive, and it's a day trip. I just haven't got around to doing it, but I do plan on popping over to Estonia at some point, but not anytime soon because I have so many travel plans right now that the idea of adding another day trip somewhere is yeah is not going to happen. Just seeing other comments here. My love life is like dark matter. They can't see me. Yes, I love those comments. Okay. Light is amazing. I agree. Absolutely. And dark matter that doesn't interact with light is even more amazing. Absolutely agree. Dark matter is very cool. It's a very fun topic. And it's a great thing to study. And there's still so many open questions about dark matter. Okay. And on the topic just now of me traveling too much, the only question I think that I haven't reacted to yet is one by David asking me if I'm going to be on next week. I will not be online for I will not be online next week for sure. And as for, Sunday 3rd, there will not be a stream. Sorry, Sunday 4th, there will not be a stream. And I also won't be changing it to the Saturday. The reason being, next week I'm heading off to a conference. So actually, I am traveling. I'm traveling there so I'm going to Norway. And rather than going to Norway by plane, because I can't directly get to the conference destination with one flight and I don't want to take two flights, instead I'm going by boat and train, which means I leave Helsinki Saturday afternoon at like 3 p.m. and I get to the final destination Monday morning at about 7:30 in the morning, and the conference starts at 12 o'clock lunchtime. So it is going to involve one night on a ferry, one night on a train. It's going to be an exhausting trip, but I am really looking forward to it because I like trains, I like boats. It sounds really fun. I'm going to be tired already when I reach the conference, but it's going to be fun. But that means that Saturday and Sunday next week I'm traveling, so I can't do a stream on either of those 2 days. Then I'll be at the conference. I'm not likely to do a stream from the conference, especially as I'm actually attending two conferences in parallel, because for some reason they decided to organize two conferences in the same university in the same week. One is very relevant to me, one is tangentially relevant, and I know people presenting there. So I'm going to be running between two conferences. Do not advise. And then I travel back on Saturday the 10th, which means I should be doing a stream. Next stream should be on Sunday, 11th of June. However, if I'm completely exhausted from the conference and everything, I might have to cancel. But technically, I will be back on the 11th of June. So that's 2 weeks from now. And I do have a bunch of guests in mind. I need to check dates with them. I don't yet know when I'm going to have the next guest on, but it's been a while since I had a guest, so that might happen soon. It's going to be fun. Getting to the destination is half the fun. I agree. I think travel counts as part of it, especially this trip. I'm really looking forward to it. It's going to be fun. I'm expecting to see some amazing scenery. I like boats. The ferry is going to be cool. And I get a morning in Stockholm. I'm sure I can squeeze in a museum in that morning in Stockholm, unless I just find a comfy chair on a sofa and chill in a cafe. But I think it's going to be fun. But yes, next stream will be 2 weeks from now on the 11th, unless I'm completely exhausted from the trips, and then I will cancel it. So, an hour and 10 minutes. Thank you, everyone, for all the questions today. This has been really fun. I like that we went on a lot of different directions, a lot of different topics, neutrino oscillations, black holes, gravitational waves, CMB physics, and the cool tangent about what would happen if we just switched off dark energy. And I still want to check the metric equations, but that was a fun tangent. And we didn't put too many animals in microwaves today, so progress from last week. This has been great fun, as always. If you have losing my voice, been speaking too much. If you haven't yet subscribed to the channel, please do so. Like the video, leave a comment, all the usual stuff. Feel free to share the video out with people. It always helps. I should be online again in 2 weeks. I hope to see you all then. And I hope in the meantime, you will stay safe and take care of each other.